Welcome back to the basic HAL tutorial for LinuxCNC. In this lesson, I want to go over the Multiplexer or MUX command as it's called. The Multiplexer command allows you to use binary data to select from a table of floating values and then output one of those floating values into LinuxCNC. And what I mean by that is if I go to these graphics here, down on the left-hand side I have this truth table. The truth table shows me 4 positions, it shows me 2 outputs, and it shows me the binary data for each of those available positions. I've got 0, 0, 1, 0, 0, 1, and 1, 1. And those 4 positions allow me to choose from 4 different floating selections and pass those selections out to LinuxCNC. If we look at this switch graphic here, we can see that we have 4 positions on the selector switch. We have position 1, position 2, position 3, and position 4. If we were to wire this switch in a 1-to-1 configuration, we would have to use 4 inputs. Input 1, 2, 3, and 4, respective to the positions on the switch. With the multiplexer setup, you basically break down your need for available inputs based on the amount of multiplexing you'll need. In the top tabs here, I have 4 examples: MUX 2, MUX 4, MUX 8, and MUX 16. A MUX 2 command will necessitate only 1 wire going from the switch to LinuxCNC. A MUX 4 requires 2 wires. A MUX 8 requires 3 wires, and a MUX 16 requires 4 wires. A MUX 16 will allow us to have 16 available floating selections to output to LinuxCNC by the use of only 4 input wires. So you can see where as the MUX grows and accumulates more available data, you're using less and less wires. Because if we were to try to wire a 16 position selector switch 1-to-1, we would need 16 available inputs. Whereas with the MUX we only need 4. So going back to this graphic here, we have a 4-position switch, and if we look at the truth table, we look at position 1, and the output going to LinuxCNC in binary form is 0, 0. If we look here, this first position lug is empty. There's no wire going out. So that's why Linux is only seeing the 0 and 0, because it's not seeing any kind of feedback from this whatsoever. Position 2 has a white wire going out to the breakout board. It's also tied in with a diode. The diode restricts current flow in a single direction. So right now, in position 2, we have a single current flow out to the breakout board. Therefore, position 2 shows a 1 for output 0 and a 0 for output 1. When we look at position 3 is tied to a green wire. The green wire goes out to the breakout board. The green wire is also tied in with the diode. The diode, again, is restricting current flow. So in position 3, we have output 0 showing 0, and output 1 showing 1. In position 4 allows current flow back through the diodes, which are then tied to the green wire and the white wire. So in position 4, it's showing true on green and true on white. So therefore, position 4 is a 1 and a 1. To show you that a little more clearly in LinuxCNC, we'll fire up our software. Take it out of eStop. Go to our HAL configuration window. And for starters, we're going to use the MUX2 command. The MUX2 command only requires a single input to choose from two floating values. In this example, I'm going to be using my PlayStation controller, like always. So we're going to use input .0, and we're going to use button A, button B, button C, and button X for all of our examples. In this case, we're only going to be using button A because we only require one button on our controller to handle the MUX2, which will allow us to select between two floating values. Think of the floating values as axis selections. If you have a rotary switch on your control panel and you want to select X, Y, or Z, or if you have a 4-axis machine, X, Y, Z, and one of your rotary axes, your A, B, or C axis. You can also use it for, you can also use multiplexing switches for your rapid overrides, feed overrides, anything that requires multiple selections and you want to kind of reduce the amount of wiring that's required for the switch to go to your board. So again, we'll show you that as an example here. I'm going to do a load RT MUX2. And then we're going to add F MUX 2.0 to our servo thread. We'll reload our HAL configuration so we can see that in our pin tree here. I've got two of these open. Get rid of that. So we have MUX2. And in MUX2 we've got MUX 2.0, in 0, in 1, a selection, and an output. We'll add those to our watch list. So right now you can see we have MUX 2.0 in 0, and that's set to a 0 value. We have MUX 2.0 .in 1 set to a 0 value, and we have MUX 2.0 .out set to a 0 value. We have MUX 2.0 .sel, which is the selection between true and false for this particular scenario. Right now it's set to false. So the first thing we want to do is we want to assign a couple of floating numeric values. Floating values allow decimals. So in this case I'm going to do a set P MUX 2.0 .in 0, and I'll say 0.1. Then I will do a set P MUX 2.0 .in 1, and we'll set that to 0.001 to differentiate between the two. If I go back to my watch list, you'll now see that I have a floating value in MUX 2.0 in 0, and I have a floating value in MUX 2.0 in 1. Right now the MUX 2.0 output is set to the value of MUX 2.0 in 0. Because the MUX 2.0, or the MUX2, is only a true or false floating output value. So right now it's set to false, so therefore the floating output value is going to be MUX 2.0 in 0. If I do a net MUX 2. Well, we'll just call it MUX 2-BTN, and we'll say input.0.button A, and that's going to go to MUX 2.0.sel. Now that we have those pins linked together I'll add the button A to my watch list. When I press button A on my PlayStation controller, you'll see that button A goes true, the MUX2 selection goes true, and the MUX output changes from the false or the in 0 to the true or in 1. So from 0.1 to 0.001. I'll reload LinuxCNC to clear out my configuration. And in this example, I'm going to show you a MUX4. Now again, a MUX4 only requires 2 actual wires going to the breakout board, say input 1 and input 2. And between those 2 inputs, we will get the ability to select between 4 floating values and pass that through to LinuxCNC as a single value. So I'll go into my configuration. I'll do a load RT MUX4, and we'll add that to our servo thread. Close out and reopen our configuration to refresh it. Go to our pins, and down in the MUX4, you'll see that we have in 0, in 1, in 2, in 3, output, SEL0, and SEL1. So looking at this MUX4, and going back to the graphic that we have here in the truth table, we have position 1, 2, 3, and 4. And then we have out 0 and out 1, which in LinuxCNC will be our SEL0 and our SEL1. So I want to assign some values to the MUX4 ins. Again, those are floating point values. So we could do set P, MUX 4.0 dot in 0. And in this situation, I'm going to break it down. I'll say 0.1, and then I'll say in 1 is 0.01, in 2 is 0.001, and in 3 is 0.0001. If I go to my watch list, you'll see that I have those 4 assignments, and right now I have MUX 4.0 out assigned to 0.1, or the 0, 0 value. So now we want to tie 2 buttons from our PlayStation controller to the MUX4 command. So I'll do the same thing as I did before. I'll do a net. I'll say MUX button 1, and we'll call it input.0.button-a, going out to MUX 4.0.SEL0 for selection 0, or the first selection. And then we will tie input.0.button-b to a net of MUX button 2, and we're going to link that to MUX 4.0.SEL1. When I go to my watch list and I bring up my inputs from my PlayStation controller, button A and button B, when I press button A, it gives me the in 1 value. It gives me 0.01 going to the output MUX 4.0.out. When I press button B, I get the third selection, or the MUX 4.0 in 2, going to the output. And then when I hold both buttons down at the same time, I'll get the fourth selection, or MUX 4.0.in 3. So again, if we look at our HAL configuration versus the truth table, for you. So here, position 1, 0, 0. Position 2, 1, 0. Position 3, 0, 1. And position 4, 1, 1. So the MUX 8 command is a little bit more of the same, but now we're adding a third selection into our multiplex. And what that will allow us to do is it'll allow us to use 3 wires to our breakout board and give us the option of up to 8 floating values within that MUX command. So I'll go back to our configuration window. We'll do a load RT MUX 8, and we'll add F MUX 8.0 to our servo thread. Reload our window. Now, just as a side note, you can have multiple MUX commands. You're not limited to just a single one. But now that we have our MUX 8 loaded, we have MUX 8.0, and we'll see here that we have in 0 through in 7. We have an output. We have SEL0, SEL1, and SEL2. In this case, we're going to use our input 0, button A, button B, and button C, because we need 3 inputs to give us the MUX selections from 0 through 7. From here, I'll start netting my MUX button 1 to input .0 button dash A to MUX 8.0 SEL0. We'll tie button B to SEL1. And we'll tie button C to SEL2. Now we need 8 different floating values. So we can go set P MUX 8.0 in 0. Let's start with 100.0, and we'll just go through and we'll say in 1 is 10, in 2 is 1, in 3 is 0.1, 4 is 0.01, 5 is 0.001, 6 is 0.0001, and 7, because I should have picked 1,000 instead of 100, we will call that 0.005. Just to throw you off a little bit. So now when I go to my watch window, you'll see I have a value of 100, 10, 1, 0.1, 0.01, 0.001, 0.0001, 0.005. The first output is going to be binary 0, 0, 0, which gives us an output of 100. As I select through the buttons on my PlayStation controller, I'll pick button A, and I'll get the multiplex value of in 1, which is 10. If I select button B, I get the multiplex value of 2, which is 1. If I select button C, I get 0.01, And you may ask why. Because it wants to see SEL0 and SEL1 go true before the third bit has a chance to activate. So it wants to see it in 0 true, 1 true, 0 and 1 true. From there it goes third true, then SEL0 and SEL2 true, which gives us our 5th position, then SEL1 and SEL2, which gives us our 6th position, and then SEL0, SEL1, and SEL2 all together to give us our 7th position. So it does get a little tricky, but you just have to remember that everything goes in an order of succession. So you have 0, 1, 0, 1, 2, 0, 2, 1, 2, 0, 1, 2. Now the MUX16 command is more of the same, but it adds a couple of different functions to the MUX command to try and smooth things out a little bit more. So there's this MUX16 use gray code, MUX16 suppress no input, and MUX16 debounce time. So the debounce time allows you to stabilize the input signals. And if you look at the help file, it says this helps to ignore noisy switches. So if you have a switch that has a little bit of noise to it, a little bit of EMI going to it, and it kind of flutters a bit. With the other MUX commands, you have a tendency of the switch being, as they say, noisy, and you might get a fluttering effect of your selection bits. The MUX16 allows you to set a debounce time which will smooth that out. So if you get that fluttering, this will help tune it out. The suppress no input allows you to set your basically your 0, 0 input to a non-input value. So when I have none of my buttons being pressed, by default the MUX 2, 4, and 8 will have the first value set as the default, whereas the MUX16 allows you to suppress the input of 0, 0 binary data, and it will stop any kind of value from being passed to that input pin. So gray code will allow you to use a different form of binary input data. If we look at the LinuxCNC help menu, we'll see that this bit will signify the use of gray code, which is actually named after somebody with the name of Gray. Gray code is, as you see here, a good choice when using physical switches because for each increment only one select input changes at a time. So what that means is that as you increment through your switch, instead of it working in the fashion of the MUX 4 or the MUX 8, where you have 0, 0, 1, 0, 0, 1, 1, 1, and then you have to enable the next bit, the third bit, and then you have 1, 0, 0, 1, 0, 1, 1, 1, 1. Instead of doing it that way, if we look at this gray code table, the difference between binary and gray code is that the first two are the same, but then as we get to the second or the third one in the order here, which is actually labeled number 2 because computers, the binary code will go 0, 1, then 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, as we saw when we were using the PlayStation controller. In gray code, it goes 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, so on and so forth. So the number tracking is a little bit different, but it kind of follows the right to left kind of fashion, as opposed to the binary code, which has to count up every time it goes through. So 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and then it can go to the fourth binary digit. It just follows a different order of succession. But again, it can be useful in the case of a rotary switch, because you don't have to make sure that your multiplex wiring ties back to those lugs with all of those different diodes and whatnot. You'd still use diodes, but the format would be a little bit different, and ultimately it would wind up being a little bit easier to connect that particular switch. The basic core values of MUX16 are going to be very similar to the 2, 4, and 8, except for this time, using it as a standard MUX16, I have 4 button assignments or 4 input assignments to my breakout board that I would be using to divide up between all the values that I have set in the MUX16. So I'll do that right here. I'll do a load RT MUX16, and I'll add F MUX 16.0 to servo thread. Get rid of this guy here. Actually, close out and reload to refresh. Going to our pin section, under MUX16.0, we have a debounce time, and then we have input 0 through input 15. So we have 15 floating input values that we can assign through the use of 4 inputs, 4 wires from a switch, or 4 buttons that we would press on our operator panel, something like that, to assign 16 different floating values. And the MUX16 also allows you to output either floating value or an S32 value. So you can output a signed integer value with the MUX16, whereas the other multiplexers were floating output only. So we have a floating output value, a signed integer value, and then we have 4 buttons that we would have to assign. So if we add these to our watch list, I'll have to net MUX button 1 to input.0.button-a, which will be MUX 16.0.SEL0. SEL1 will be button B, and we'll call that MUX button 2. MUX button 3 will be button C, and that will be SEL2. And SEL3 will be button X. And we'll call that net MUX button 4. So down here, I have A, I have B, I have C, and I have X. For each of the input values, I set p mux16.0.in0. Here we'll just give it, let's give them integer values, signed integer values. We'll say 1, in 0, 0. We'll set 0, 1 to -1. We'll set in 2 to +2. In 3 to -2. In 4 to 0.1. In 5 to -0.1. And you don't necessarily have to use all of the MUX selections, but if we show you here, the first 4 are going to be basic like you would on a MUX 4. It would be, if we look at our values down here, our output values, our SEL 0 right now is set to +1. SEL 0 true makes it -1. SEL 1 makes it 2. And then SEL 0 and 1 together makes it -2. If we go into input 4, which is button C, we get the 4th value of 0.1. If we go SEL 2 and SEL 0, we get value 5. So it just stacks on from where we were, and it just keeps adding and adding and adding to that in that same order of succession. So input 6 will say +0.01, and input 7 will be -8 will be +0.001, 9 will be -10 will be 0.001 positive, 11 will be negative, and then 12 we can add different values to it. We'll go 10. 13 will be -10. 14 will be +20. 15 -20. And that should be all of our assignments. I'll maximize the window so we can see all of the different values. And then down at the bottom, we can see our selections. SEL 0 gives us a current value of 1, making it true, makes it go to -1. SEL 1 true makes it +2. Both of them together, -2. SEL 3, +0.1. SEL 2 is +1. SEL 2 with SEL 0 is -1. SEL 2 and SEL 1 is 0.01. SEL 0, 1, and 2 is -0.01. So at this point we're at MUX 16.0.in07. To go to the 8th one, we'll use the SEL 3 button, which is button X, to get to in 8, which is 0.001. And then from there it just adds on. So we'll go to SEL 0, which is -0.001. SEL 1, which is 0.0001. SEL 0 and 1, which is -0.0001. And then we'll have SEL3 and SEL2, which gives us the 10 value. SEL2, SEL3, and SEL0 gives us the minus 10 value, which is 13. If we select SEL1, we get the 14 value of 20, and then we light them all up together, and we get the value of negative 20. So it does tend to get a little confusing when you get that many multiplexers going together. But again, the benefit of it is that we have 16 selections that we can choose from, utilizing 4 wires to our breakout board, only utilizing 4 inputs. So we have 16 options with just 4 inputs being set to true or false. This is a good way to have multiple assignments and utilize a minimum number of inputs to your board, because believe me, you can run out very quickly. So last but not least, I want to briefly go over the MUX generic command. The MUX generic command is different than the other MUX commands that we've just covered, because those MUX commands are pretty specific for the type of input data and output data that they require. The MUX generic command allows you to choose the type of data that you bring in and the type of data that you send out. The type of data you can bring in or send out will be bit, floating point value, signed integer value, or unsigned integer value. So you can bring in any of those values and send out any of those values. The format is loadRT, MUX generic, config equals, and then in double quotes, you put in the type of data you're bringing in, the type of data you're sending out, and the amount of inputs that you're going to require for that MUX generic. If you separate multiple MUX generic commands with a comma, you can create multiple MUX generic commands within your HAL configuration. So to show you an example, we'll launch LinuxCNC. Go to our configuration window. And we'll do a load RT MUX underscore generic config equals, and then in double quotes, we'll say, to keep it simple, we'll do B, F, and we'll say 32. Close, reload to refresh. Go to our pin section under MUX generic 00. You'll see that we get 32 input bits. We have an out floating bit, and then we get our SEL bits 0, 1, 2, 3, and 4. So when you need a larger MUX than a MUX 16 will provide you, you can use MUX generic to create a multiplexer of any size or complexity that you require. If you don't use the MUX generic with a binary input, floating output, and then a multiplier of 2, 4, 8, 16, 32, chances are you won't get the selection 0 through whatever, the SELs. I'll show you that. If you try to use it for some random values, you'll get only a hexadecimal input and not the binary data input. So we'll do it again. Load RT, MUX, generic, config equals. Let's do unsigned input, assigned output, and a value of 7. We'll close, reload, go to our pin section, under MUX generic 00. Now you'll see that we get unsigned integer values that come in with a hexadecimal input, assigned output that is assigned integer value, and an SEL integer that is a hexadecimal value as well. Honestly, I haven't really played around with that enough to grasp a full understanding of what that is going to require to make work. I do know that I can utilize the MUX generic again for more I/O than is standard with the MUX 2 through 16s. But when it gets to the hexadecimal stuff, I haven't really touched that as of yet. But let's go a little crazy. And we'll do a load RT MUX generic with a config of BF. Let's try 64. Refresh. And we'll see 0 through 63 with select bit 0 through 5. So we have 6 wires that we would use to control 64 different I/O settings through this multiplexer. Again, it's a useful tool for multiple selections with a reduced amount of inputs or reduced amount of wires. You still get the unsigned integer selection here as well, but again, I haven't really tackled that as of yet. So that pretty much concludes my tutorial on the multiplexer command. This is something that really threw me for a loop until I was able to sit down with it, break it down step by step, and see exactly what it was doing. And once I saw what it could do, and the fact that it was minimizing the number of wires that I needed to send to inputs and minimizing the subsequent number of inputs that I needed to my board, I did definitely see a great deal of usefulness to this command. And future video will include me, again, using an axis selection switch and using a multiplexer to select between my X, my Y, my Z, and potentially my A axis if I put a rotary table on the machine. And in that case, I would use a MUX 4 because I would have 4 different selections but only require two wires going to 2 inputs instead of having to have 4 individual inputs. And with that, if I wanted to use a feed override knob, I would use probably a MUX 8 or a MUX 16 and then have that many positions available for my rapid or my feed override. In my case, I'm going to be using potentiometers, so I'm using the analog input settings on my Mesa card to eliminate having to use multiplex switches or have that many inputs going to a single switch with one-to-one to each position. So again, thank you for watching. Please be sure to like and subscribe if you're enjoying the content. Please let me know what else I can do tutorial videos on, what is stumping you, what's keeping you from absolutely loving LinuxCNC. Because the more I use it and the more I make videos for you guys to watch and learn, the more I'm enjoying using LinuxCNC and the more it's inspiring me to learn more about it so I can show you guys. So just let me know in the comments what you'd like to see in upcoming videos, and I'll try and get to them as quickly as possible. Thank you for watching, and hope to see you soon.